In this video, we're going to do one more 3D rigid body equilibrium problem, just in case you need a little bit more practice. We already did a couple, but here's one more extra example problem. And what we're looking at is this curved bar. We're told that it's supported by a journal bearing at A. Remember, journal bearing, it's free to slide along the axis, along the pole. And we've also got a cable from B to C and a cable from B to D. And we've got a couple of forces, an F1 that's downward and an F2 that's pointed in the positive Y direction. So first thing we're going to need is a quick free body diagram or bar. It's I'll try to draw it in kind of a similar orientation to the original picture. Looks like that. We'll put on the original forces that we know. We've got downward 800 newtons and off in this direction, we've got 350 newtons. We've also got two tensions. We've got, I'll make those a different color. Tension in cable BC. And in this other direction, we've got a tension in cable BD. And then at our journal bearing, remember what a journal bearing does is, because we've only got one bearing, we want to go and look up which moments and which forces will be on this bearing. So what this bearing is going to do is it's going to prevent translation in just two directions. Since it's a journal bearing, it's free to slide in the Y direction, which means we're going to end up with a reaction in only the X and the Z directions, but not the Y direction. If it were a thrust bearing, we would also have a Y. And then because we only have a single bearing, that bearing is also capable of preventing rotation, right? This bar is free to rotate about the bearing at A, about the Y-axis, but that's going to prevent it from rotating about the X-axis and the Z-axis. So what I want to do is draw on here a moment at point A about the X-axis and a moment about point A about the Z-axis. So we've got two unknown moments and two unknown forces at a single journal bearing. If we'd had a pair of journal bearings here, then we wouldn't put any of those unknown reaction moments on there. But looking at my picture, I'm counting two tensions, two reaction forces at the bearing, and two reaction moments at the bearing. So that looks to me like I've got 6 unknowns, and it's a 3-dimensional problem, so I can write 6 equations. So we should be able to solve it. All right. In order to start the problem, I need to write my tensions. Everything is just normally in the X and Y and Z directions, except for those two tensions in the cable. So let me write those as Cartesian vectors. So the vector tension in BC is going to have a magnitude that I'll need to solve for, but the direction I know. And to go from B to C, this is a little difficult to see in this picture, but it looks like what they're trying to tell me by this Y-axis and this Z-axis right here, and then showing that C and D line up with it. It looks to me like C and D are just in the same YZ plane as point B. So there's no X component to those two tensions. This one I honestly think is really hard to visualize, but that's what they're trying to say by the fact that these Y distances from point C and point D just go right back to that Z-axis that goes through point B. So we're going to say that this tension has no distance in the X direction. Going from B to C, I do have to go minus 3 meters in the J direction. That's this 3 meters right here. And I have to go up, looks like 4 meters in the K direction. So there's the position vector from B to C. I want the unit vector, so I need to divide by the length of that vector. So that's going to be the square root of 0 squared plus 3 meters squared plus 4 meters squared, which you add that up, 9 plus 16 is 25, square root it, and you get 5. So this is going to end up being tension in BC times nothing in the I direction, and I've got a minus 3/5 J plus 4/5 K. All right, same thing for the other tension. Tension in cable BD. It's got a magnitude I'll need to solve for. It also has 0 in the I direction. This one is actually coming from B to D, we've got to go up plus 3 meters in the J direction, and finally plus 4 meters in the K direction. And we divide that by, same thing, square root of 5 meters is the total length of the cables. Meters all cancel, and we get that the force in cable BD has a magnitude times 3/5 J plus 4/5 K. So just like the other tension, except one of the signs changes for the Y component. Now let's go do equilibrium equations. And you know what I just noticed? One of our numbers we can find right away. You'll notice the applied forces are both in the J and the K direction. And we just found out that those tensions only have J and K components. So the only force on our entire body in the X direction is AX. So I can immediately just sum forces in the X direction, and I get that AX is the only force in the X direction has to be equal to 0. And we just found one of our 6 unknowns. That's great news. We only have 5 to go. If I sum forces in the Y direction, I'm going to use this equation eventually. That way we'll call positive. We've got our applied 350 Newton load that was applied, F2. And then I'm going to need the component of TBC, which is a minus TBC times, well, I'll write it minus 3/5 TBC. And then plus 3/5 TBD equals 0. So there's an equation I will use later. And I can also sum forces in the Z direction. Pick a sign convention, typically upward is positive. I've got a minus 800 newtons, that's from F1. I'll have a plus 4/5 TBC plus 4/5 TBD. And then finally, I have an AZ plus AZ equals 0. So these are 2 perfectly fine equations. They're not very helpful right now because those 2 equations have 3 unknowns combined. So let's go sum moments. Good candidates for summing moments would be axes that will eliminate a lot of unknowns. And when I look at this picture, I like the idea of summing moments about the y-axis, because the y-axis goes right through point A, and there is no reaction moment at A about the y-axis because it's a journal bearing. So I want to sum moments about the y-axis because the only 2 unknowns that will show up will be TBC and TBD. And then this 800 Newton will also create a moment about the y-axis, but AZ and AX will not because they go right through the y-axis, and you don't include a moment about the X or the moment about the Z-axis in a moment about the y-axis equation. So let's try that one next. We want to sum moments about the y-axis equals 0. Using right-hand rule, my thumb would point along the positive y-axis and my fingers curl in the direction of the positive moment. I want to do this 2 different ways. Because I know some of you are more comfortable with just trying to visualize these, and others would prefer to just let the cross product do all of the work. All of the forces are exactly 2 meters away from the y-axis, right? And if I look at this picture, that 800 Newton force is 2 meters away. It is going to cause a positive moment about the y-axis. So I can just write this down as 800 newtons times 2 meters. That's a positive moment. And then if I look at TBC and TBD, remember these guys only have a Y and a Z component. Their Y components that are in this direction, they cause no moment about the Y-axis because they're parallel to it. Their Z components are both upward, and their perpendicular distance from the Y-axis is the same 2 meters as we had before, and they're going to cause a negative moment about the Y-axis, right? They tend to rotate around that Y-axis, so that if you were curling your fingers in the way they tend to cause this part to rotate, your thumb points in the negative Y direction. So what I want to add on here is the Z components. So 4/5 TBC times 2 meters. Oh, I made a mistake. I wrote plus. This should be minus. These moments are in the opposite direction of that 800 Newton times 2 meter moment. And then I'll also have a minus 4/5 TBC, which is also 2 meters away, equal to 0. And there is your moment equation, just looking at the problem, looking at the components of the forces and visualizing what direction moment will they cause and which components will cause a moment. Before we solve this, I actually want to write this out using cross products. So if I'm finding moments about the y-axis, I need to put a 0, 1, 0 in my top row. Remember, because the top row is the axis. You need a unit vector pointing on the axis. So for y-axis, it's just j. That middle row becomes your position vector. This position vector was 2 meters in the x direction. And when you start at the axis and go out to the point where these forces occur, you're going in the positive 2 meters. So I plug in 2 meters, 0, 0. And finally, my force, this first force was a negative 800K. 0, 0, minus 800 newtons. So that cross product will give me the moment about the y-axis caused by the downward 800 Newton force. Plus, top two rows are going to be exactly the same, 0, 1, 0. And 2 meters, 0, 0. But now we're going to plug in tension in BC. Tension in BC has the 0 minus 3/5 TBC plus 4/5 TBC. And finally, 0, 1, 0, 2 meters, 0, 0, 0 plus 3/5 TBC plus 4/5 T. Oh, this is not BC. The second one is BD, and I made the mistake up above too. This should have been a BD, and this one should also be a BD. TBD. So we have our three cross products. They're super simple because they have so many zeros in them. The reason the first two rows look the same, the first row should always look the same because we're summing moments about the y-axis for all of them. Because they all have 2 meters is because all three of these forces live at the exact same location. If they were at different x distances from the y-axis, they'd have a different position vector, but these are all at the same location. So when we go to do our cross product, so remember how I like to do cross products? I take the whole thing, copy, paste it, and then I copy the first two, paste them to the side, and then I do my basket weaving process. So those three, which is a 0, plus those three, which is another 0, plus those three, which is another 0. Then I do my minus signs, other direction. We got minus 0, minus 0, finally minus 1 times 2 meters times minus 800 newtons, giving me the exact same answer. It ends up being 800 newtons times 2 meters that I had up here. So I got it by just visualizing the direction of the moment that force would cause, or you get it from your cross product right here. I can do the same thing with the other two. I will do it for one of them. So we take that. We take our first two columns like that. Start with my purple positive ones. We got a 0, 0, 0. I should add those, huh? 0, these are all being added. 0 plus 0 plus 0. Now I'll switch colors, go the other direction, and I've got minus 0, minus 0, minus 1 times 2 meters. This is coming from this last one, times my positive 4/5 TBC. Okay, and this ends up matching exactly with what I had right up here, minus 4/5 TBC times 2 meters. And if I do the third one, I'll get the third term. So just trying to build some confidence that you can use cross products and it will work, or you can just look visually at which force components will cause which moment and will it be positive or negative using the right hand rule. All right, so let's go solve the problem now. We've got a summation of moments off the y-axis. It looks good. It's got TBC and TBD in it. So I'm going to want to take that equation, maybe call this my star equation, and up here call this my star-star equation. And I want to combine them because they have the same two unknowns. So I'm going to just copy these guys down again, take in this equation, copy and paste, that's my star equation. And then I'm going to take my second one, is right here. Paste it, and I need to solve these two equations for the two unknowns. I think what I'm going to do first is I'm going to cancel out these 2 meters, make life a little bit easier. And if I multiply the first equation by 5/3 and the second equation by 5/4, so let's do that. I'm going to take this first equation, times it by 5/3, second equation, times it by 5/4. That first equation becomes 583.33333 newtons minus TBC plus TBD equals 0. Second equation becomes 1000 newtons minus TBC minus TBD equals 0. And here's what's beautiful. I can just add those two equations up, and I get 1,583 newtons minus 2 TBC plus 0 equals 0. And I solve for TBC, 791.67. So around at 792 newtons. I just substitute that right back in to either of these equations and solve for TBD. So TBD, I'll take the is equal to 1,000 newtons minus TBC, and I get 208 newtons. We found our two tensions. We've already back up here at the top found AX. Now that I know both those tensions, I can plug into my sum of forces in the Z equation to find AZ. Copy this, bring it down here, run through the numbers. We'll just rearrange it first. I make fewer mistakes if I actually write these steps down. AZ is equal to 800 newtons minus 4/5 TBC minus 4/5 TBD. So plug them all in, minus 799.7 newtons. So with rounding error, AZ is actually 0. AX was also 0. The two tensions we've got. So the only thing that we have left to solve for are those reaction moments. So how do we solve for reaction moments? The only way to solve for them is using a moment equation. So we need to sum moments about an x-axis and some moments about the z-axis. So starting with the x-axis, what do we have for x-axis? I got to find my drawing again. You can choose whether you want to sum moments about the x-axis, this global x-axis over here, or the x-axis that goes through point B. And here is a hint. It'll be way, way, way easier if we pick an x-axis over here, because guess what? Look, then this 350 Newton won't cause a moment. It goes right through it. This 800 Newton won't cause a moment. It goes right through it. These two tensions won't cause a moment because they go right through that axis. AZ and AX were already 0. So if we sum moments about that axis, the only moment that will show up is MAX. Remember, MAX is a couple. So any x-axis that you sum moments about, it can be the x-axis through point A, through point B, through point D, through point C. It doesn't matter where you sum moments about. You have to include that couple moment because couples act kind of on the entire system globally. So maybe a way to think of it. So I'm going to do the math really easily. We are summing moments about the x-axis through point B, that red x-axis that I drew. And what you get is the only moment that shows up is MAX, and it has to equal 0. Which is a good idea because if your bearing has a really big moment on it, it's going to wear out really fast. Let's try Z. Summation of moments about the Z-axis has to be 0. Now let's go pick a convenient Z-axis to sum moments about. So back up to my problem, I can use this Z-axis, the global Z-axis if I'd like. That doesn't help a whole lot with these forces over here. I'm going to have to include some of those components as a moment about the Z-axis. Or the most clever thing to do is probably, is there a color I haven't used yet? Hot pink. Let's take this Z-axis right here. If I take this Z-axis right through there, then well, this guy wasn't going to cause a moment anyway because it's parallel to the Z-axis. Neither of these tensions will cause a moment because they are going right through that z-axis. Again, AX and AZ were already both 0, so they won't cause a moment. So the only thing we'll have causing a moment is this 350 Newton. And it will cause a moment because it is not parallel to the z-axis, doesn't pass through this pink z-axis, and it's a distance away of 2 meters. And it looks to me, if I start at that axis, my fingers have to go in the negative x direction. And then if they curl in the direction of that force, this is actually going to cause, my thumb will be pointing downward. It ends up with the right hand rule causing a negative moment about the z-axis. So let's go do that summation. So what we'll have in our moment about the z-axis is I will have MAZ that I need to solve for, plus the moment caused by that 350 Newton force. And that's gonna actually have a negative. I'm just looking at the picture, it's gonna cause a negative 350 Newtons times 2 meters away from the axis, and that equals 0. And you solve it, you get that MAZ is a 700 Newton meter reaction couple that has to act to hold this whole system in equilibrium. Okay, if you couldn't visualize that 350 Newtons would cause would cause a negative moment, you can certainly use a cross product for that. The cross product would look like this. We're finding a moment about an axis aligned with the z direction. So your first row becomes the 0, 0, 1. Your second row is the position vector. So if you start at the axis, which is out at point B, we're summing the moments again about z-axis through point B. Well, to get from that axis, this is, I think, a hot pink axis, right? To get from that hot pink axis back to the force, we have to go in the negative x direction. So we're going to write this down as a minus 2 meters, 0, 0. And finally, the force is a 350 Newton, 0 force. It's pointed in the positive y direction. All right, let's run through the numbers really fast. We do the downward diagonals first. We've got 0. Oh, I forgot to copy them. We'll copy them. Copy the columns. Copy, paste. So we do that one, gives us a 0. That one gives us another 0. That one gives us a 1 times minus 2 meters times 350 Newtons. And then we go back the other direction with the negatives. We got 0, so minus 0, minus 0, minus 0. These are zeros because if anything along the diagonals is 0, we're multiplying all three of these numbers together, you get a 0. So the result, this is the moment, ends up being a minus. We get the minus sign right there. And that matches what I put up here. All right, hopefully this was a helpful, kind of detailed example of how we can solve for all of the reactions for a fairly complicated 3D rigid body equilibrium problem.